Okay, so differential equations are equations in which derivatives of an unknown function y equals f of t occur. So let's look at some examples. So one example would be if we have a derivative of y is equal to 6t plus 3. That would be 1 there. These should be familiar to you. And it's not these equations, these are arbitrary, random, but the pattern should be familiar. Let's say we have y prime equals, say 6t. Let's see if I have any sign or I do not, but let's do this one. Prime plus 3y plus t equals 0. There's a variety of forms these can take. But you're still probably not sure what is the physical significance of these. Like I said, I wasn't when I first studied these. And being that we're in physics class, we should say, how can we apply these to physics? And since we know physics applies to all the physical phenomena of the world around us, let's try to guess or examine what a few differential equations would describe. The easiest way to pick something in physics, and this should be indicative of the whole pattern here, is to look around you. Look at everything that's going on in this room right now. And in one way or another, you can describe it by a differential equation. You really, really can. So let's do some things specific to you right now. Let's say your position in the school is dependent upon a factor of what time of day it is. So where you're likely to be at or where you should be at depends on what session it is, what period it is, and that would help me determine your position. So in other words, your change in position over time, or your change in where you're at versus some amount of day, is dependent on the schedule here at school. How fast you're traveling in a car depends on a bunch of different factors, of course, but let's make it easier. Let's say the position of where you're driving at and the time of day. Who's driven through like the Squirrel Hill Tunnel in Pittsburgh? Who's driven through there during rush hour?
Me, it's crazy.
It's crazy, right? So how fast you go through that position depends on the time of day. So again, you're talking about your change in your speed depends on two factors. Where exactly you're driving. If you're on a highway where the speed limit is 65 miles per hour, if you're on a dirt road where you're trying to keep it slowed down so you don't crack an axle or something or damage your car, and you're going 15 miles an hour, it depends where you're at. And also depends on the time of day. And if it's rush hour, there's no way you're going to be moving as fast as if it wasn't rush hour. Let's look at some astronomy things. If you're curious enough and you go outside at night and you look up at the sky, you'll see all these little lights up there. With the exception of the planets, we call those stars in the sky. And if you're out there watching long enough, you'll see that they actually move in the sky over the course of the night because the Earth itself is spinning, and that changes your perspective of where these stars are to you in the sky. So their X position might change. If you would lay an axis over the sky, their X position might change. Their Y position might change up there. Or even their Z position, because this is three-dimensional things up there, might change with time too. And in fact, one of those might change just by itself and keep the other ones the same. And in calculus, we actually have a name for that, and that's called a partial derivative, which you haven't, I don't imagine you've done yet in calculus. But you can change one variable and keep the other ones the same. And again, that's a partial derivative. But those are all examples of differential equations. So in physics, we might see something along the lines of dx dt is equal to some function that has two factors. position again and time. Because you know in here, if you've been paying attention all year, you know that we talk about position and time a lot. And if we combine those two things, we can note velocity and we can note acceleration and a whole myriad of other things just by position and time. And in fact, I can say that if you know something's position and you know its momentum in classical physics, you know everything about it. You know its energy, you know where it'll be. Every little thing can be determined by those two factors. So that's why this is so common. That's why we see differential equations in physics so often. So if we just want to be descriptive here, we'll say X, what are you, on a hill? You know? A tunnel? These things would change or alter your rate of change with respect to time, because of course if you're on a hill and you're not changing how much you're pressing down and accelerating your car, you're going to go slower. Or if you're going downhill without changing it, you're going to speed up. So sometimes in math and physics you can have a description of something that involves two factors. And you've seen this, you just haven't seen this one, as I've said already. Alright. Any questions on what a differential equation is? Some examples of here how we would usually see it presented in physics. Anything on that?
No.
So we want to try to use these and so on, alright? Good, 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 good.
I'm sorry, I interrupted here.
That's okay.
Yes.
Don't think I need to. Alright, so one thing that we do to use differential equations is that we look for solutions to them. Solutions to differential equations. So, the whole gist of this is that we're using some function and a number of its derivatives. We'll say involved instead. It involves a function y and its derivatives. Y prime, y double prime, third derivative, and so on. For a solution, we can suppose that y is a function of t. Could be time, could be anything else, but we're using t. Really quickly, again, I'm always recalling back to what I was like when I was doing this stuff for the first time. When we say y is a function of t, what are we saying about y? What does that mean? Like when we see something that's a function, something that's a function of x, what does that mean?
Y. It's just Y.
Yes, yeah. So in this case we're using, well here we would say the function is dependent upon x, here we're using y and t. Here we're saying that y changes, or the changes in y occur as we put in different values of t. Yeah, as t changes, we'll get different things for y. So we can use a physical example here. If we're walking down the hall, our position changes as a function, or one of the ways we can describe it, as a function of how much time has passed. Because if you're moving with a constant velocity, and you know how much time has passed, you'll know how much your position has changed. So, That's what we're saying. So suppose that y is a function of t. We could say time, position in time. So if we suppose that this makes any function say f of t, any function a solution any function f of t a solution such that the differential equation. So we've gotten to the point where we're taking a derivative here, or we're given an equation that has a derivative. Becomes true when y is replaced by f of t. So, if we have y prime, let's say y prime and f prime of t, y double prime and f double prime of t, and so on and so forth. So this is sort of almost like a check in a way. So we can find a solution. And I understand this word might be kind of strange using this context. And I think all of your experience in math so far, when someone says, you know, what's the solution, you're thinking of like, well, 7 plus 3 is 10, so 10 is the solution of that equation. We're expanding that definition now for you. It's no longer that simple case where it's very limited to one respect. We're giving you a whole wider range to use this language here. So a solution in this case would be when you have a derivative of some function, and you have a known function, and when you take the derivative of that known function, you can substitute it in for y, and the equation still makes sense. So we have a function here, some given function, might, could be a derivative or something involving y, and we have another one, and if we tweak that, we can put one function in place of the other one, and it still satisfies it, so that function that we're plugging in is a solution because it works. You still get the same answer when you replace it for what was in there originally. So in other words, you're finding out values of y. What does y equal, or what does y prime equal? You can do that. It's very efficient, and I'll tell you where I've come across it a lot. Outside of classical mechanics, we're talking about motion and all those things, you come across a lot in quantum mechanics, or even in electromagnetism. So a lot of times you're given complex functions there, and you're looking for one set of solutions that satisfy that. So if you use this technique of solving differential equations, you can get solutions that you're looking for. They're particularly helpful, like predicting where a particle is going to be. Where's an electron going to be around an atom? You can use a differential equation solution to figure that out. We can get into a whole mess with quantum mechanics here, and I could share with you really great experiments at some time, but we'll save that. We'll save that for the future. Creating board space. Let's do our first example. Example 1. Show that f of t equals 5e to the negative 2t is a solution to the differential equation y prime plus 2y equals 0. So based on this over here, and this is just, you haven't done it yet, but let's just see. How do you think I should attack this, or how would you attack it? Keeping in mind, of course, that we're trying to match up, say, this function, where it matches up with just the function of y, or the derivative of this function matches up with just the derivative of y. What should I do?
Could you start by solving the bottom equation for y prime and then plugging f of t in for the y?
You know what? That's a fine place to start, but we don't even have to. You wanted to like move 2y over here?
Yeah.
We don't even have to do that. I mean, we could. We don't have to right now. But we definitely are going to be plugging in this function in for y. So based on that, I'll write it in. So our solution. We have y prime plus 2 times our function here. 5e to the negative 2t equals 0. So, right here, this is just y. So we've made that substitution. Put the function in here into its corresponding power of derivative, or in this case, non-derivative, in our equation. And that's step 1. Now we have this y prime here. No, just take a guess. Guess has never hurt anyone.
We deliberated that y and plugged it to the y deliberated.
What's that? One more time.
We deliberated y, did we?
Take the derivative?
Yeah.
So you want me to take the derivative of this?
Yes.
Very good. So I'll do it over here on the side. So f of t is 5e to the negative 2t. F prime of t becomes what? Are we at all familiar with taking derivatives of exponential functions?
It's just like a normal derivative.
This is a normal derivative.
So it would be negative 10 e to the negative 3
Negative 10e.
to the negative 3.
And
T.
minus 2
Do you have to bring
t
the
plus,
t down?
oh, minus 1.
Yeah, I did have to bring the t down.
That's fine. Minus 1. Right? Yeah.
There we go.
That's it?
That's it.
Don't you have to
It
take...
just shows.
Yes. So when you have an exponential, what you do is you take this, you bring it down, and you take the derivative of that. So if I brought negative 2t down here, of course there's a 5 here before, and I took the derivative of that with respect to t, I would just have negative 2. So negative 2 times 5 is negative 10. And then the other little trick is, whatever was up here, you just leave it the same.
What's the thing that we minus 1 on the exponent?
That
That's the second one.
No, that's what you do in the case if it's like x squared. So if you have f of x equals x squared, and you take the derivative of that, you would get 2x minus 1 off there, so it'd just be.
Right. But we
In
don't
the
do
case
that
of these
with-
exponential functions,
So when
that's
you
just
have...
something that you put in here.
So when
the
you
old
have...
memory bank there for later. When you see an e, you bring it down, treat it like a normal function by itself,
like that.
do what you have to do, and then just leave this part of it alone. You just put it back. Bring it down, do what you want, put it back. Use it, put it back.
So that's if there's an e in the equation.
Yes. Yes.
If there's there's none, you then we bring it down.
And subtract 1, subtract 1.
Keep it out of the top.
On these problems, all we're doing is like proving that it's true.
You got it. You're seeing that this function is a solution to this. So now we have the derivative. And just like how we put the original function in for the non-derivative y here, we're going to put this in for y prime over there. So now this becomes negative 10e to the negative 2t plus 2 times this is just 10e to the negative 2t. Does this in fact equal 0?
Yes.
Very good. So, therefore, f of t equals 5e to the negative 2t is a solution. Wonderful. See, not that bad. You're just matching up derivatives, or in this case, non-derivatives, and you're just putting them in their place and seeing if it works.
Why don't we take the t down? The minus isn't it supposed to be?
Right here?
Yeah.
Well, let's say, remember I said you just bring it down and use it then? So I'm just going to highlight the fact that we had a 5 here before. Okay. So we bring down negative 2t times 5, in other words. So let's combine 2 and 5 just by distributing it in there. We have negative 10t, and I said, okay, now take the derivative of this with respect to t. You would just get negative 10. And then that's what we see here.
Okay.
And then, like I said, you've used it, and then you put it back. So that's why the t goes away. That's why there's no t, because you're bringing it down, take the derivative of that, put it back. Any other questions for this one? We'll do one more. You can go. The notes will be available on home. All right, example 2. Same thing. Show that f of t equals. I've made this one a bit more interesting, I think. 1/9 t plus the sine of 3t is a solution to the, I'm going to leave out the word the there, to the differential equation, and I think I gave this one a double derivative, y prime plus 9y equals t this time. Alright, now, I put a trig function in here. Who here gets a little bit scared when they see a trig function? Because I know when I started out the same way. And in fact, sometimes depending on the trig function, I still feel like that. If I see like cosecant squared there, like, what do I do with that? And you have to go back and look at your old identities that you haven't looked at in years, and you see that it's you can put in something that's more familiar to you. But the more you do them, the easier it is, and the more familiar they become. And when you see things like this, you're like, oh, my good friend, the sine function. I know, son. We hang out on the weekends. All right, so let's do a solution now. So what should I do this time? I'll give you a hint. I'm doing the same thing as example 1.
Could you take your f of t first?
Okay, so I can take the derivative. Is there anything in here that is
You need to take the
first
second
derivative?
derivative.
Just y.
Well, is this a derivative? Does it have the prime by it?
No,
No, it's just the original function.
the y.
So should I do just the first derivative, or should
Take
I
the
do
second derivative.
second? Yes, double derivative. So let's do that over here.
I'm taking the double derivative of f15.
Yes. So f prime of t. Anybody want to help me out here? Let's do it piece by piece.
1/9.
What's the derivative of 1/9 y? What'd you say?
1/9
1/9. Very good. 1/9. All right.
plus
Sine of 3t.
cos 3t.
So it's definitely the derivative of the sine is the cosine. Now what do I do with that pesky 3?
Doesn't it?
Stick it out in front.
It's a constant, so you can move it.
We're not doing, again, we're going to take the derivative, or we're going to bring it up, use it, and put it back. So the derivative of 3t is 3. Cosine 3t. Very nice. I think the other way you do this might be like by substitution, but once you've done them for so long, you know the pattern, and that just takes time.
Quick question.
Yes.
The derivative of sine is cosine.
Yes.
And derivative of cos is minus sine,
You
right?
got it.